video, we are going to discuss the Learning Target D10 guided study. Learning Target D10 is local linearization, where we are going to create a linear approximation to basic functions and then compare actual values to approximate values using the linearization approximation. But before we do, my intention behind this video for this specific guided study is to review some past concepts in order to draw some connections between what we've learned and see where a lot of the questions you're being asked are very similar. First, if you remember learning target L1, this is the secant slope, tangent slope learning target. This is the learning target where we picked 3 points and made 3 secant slope approximations and then used that information to conjecture the tangent slope. The secret is, though, now that we've learned derivatives, we can just find the tangent slope. And that's kind of what I'm trying to get at with this guided study video. Because from learning target D1, remember that's when we used the limit definition of the derivative. And this created a formula using limits, which we learned about really in all of L1 through L4. But it used the idea of limits to find a formula for the derivative. And if you recall, we found the limit as the interval between secant line points went to 0 of the difference quotient, which the difference quotient is exactly what we use to find the secant slope. I'm going to write this formula down in a little bit. Then recall from learning target D3, we stated that the derivative represents the slope of the tangent line of a function at a point x equals a. So it was at that point where we actually said the derivative is the slope of the tangent. And this is the learning target where, remember, we brought together the increasing, decreasing behavior of f of x. So f of x is increasing if the value of the derivative is greater than 0. And then f of x is decreasing if the value of the derivative is less than 0. So if we can take the derivative on an interval of the function f and find its value on that interval, so its value at any point, then if that value is positive, we know the function has increasing behavior. The function, not the derivative. And likewise, if we take the function's derivative on an interval and evaluate it at a point on that interval and we find that it's negative, we know the function is decreasing. And then we kind of said it, we kind of alluded to it, but we're really going to talk about this coming up in the applications of derivatives sections. But when f prime equals 0, there's a horizontal tangency. So the line, tangent line to the graph at any point x, it has to be at a specific point. You have to find that or be given that. Then you know there's a horizontal tangency. There's a flat line. The line y equals a constant is a tangency to that point. Then we went through several learning targets D4 through D8, to learn quick, and I put it in quotes because everybody knows the quotient rule ain't quick, but to learn quick formulas and procedures for finding derivatives of functions. And this prevents us from having to use the limit definition of the derivative every single time we want to take a derivative. Nobody wants to do that, not even me. And I love math. But those quick formulas gave us the ability to find f prime given a function f of x, any function f of x. And then again, we can find the value of that derivative by plugging in a specific x value, and we can decide if the function itself, the one we took the derivative of, is increasing or decreasing. So in introducing learning target D10, which is called local linearization, really I want to say first, we're not doing anything different than we've done before. It's called local linearization, but all that really means is finding a tangent line. We're just now going to extend the idea of finding a tangent line to something called local linearization, and we're going to use this local linearization to approximate the function. We're actually going to use that line to make guesses about what the function value could be near the point where we linearize. I'm going to write this down because it's important. Now for these, when we linearize, we will need to be given a function and a point. And you see this a lot. Given f of x and x equals a is going to be the point where we linearize. And I'm going to explain what that means in class, in lecture, for sure. But just have that idea in your mind as we continue. Now, again, as I said, this is no different than finding tangent lines, which we've already done several times. We've already found equations for tangent lines up to now. So in order to help kind of remind us what we've used to do this, there's two forms of the equation of a line, but I really want to point out that these two forms are not different. They're the same, they would be the same line for any function and any point A, but they're just written differently, and I'm going to show you how to go from one to the other. The point slope form of the equation of a line requires you to find or be given the slope and a point on the line. The point on the line will denote x naught, y naught. So the point slope form of the equation of the line is y minus y naught equals m times x minus x naught. Now, for that exact same scenario, if you distribute m and add over y naught, you're actually finding the slope-intercept form. So if we distribute m and add over y naught, this is the variable, so this is the slope times the variable, and this is a constant. This is actually b. That value there is b for slope-intercept form, which was y equals mx plus b. So when asked to find the equation of a line, you can use either one. Typically, especially like an online system, if you're submitting homework online, will probably want you to find the m and b values. It might even specifically ask you for the m and b values. But for me, you don't have to. And actually, I'm going to show you in a minute that this is the exact same formula that we're going to use for the local linearization. We're just going to rename some of these things. We're going to be given a, so x naught is going to equal a. And then y naught, well, it's the y value at x naught. So it's f of a. That's really all this equals. X naught, y naught. That's all that equals is a f of a in what we're going to use later. So in a minute, we're going to see that formula, but first I want to go back to an example from L1. So if anybody is still having difficulty getting this point or this expertise point on a checkpoint, we're going to review it now, so hopefully this will refresh the concept and help you out there. So let's look at the function f of x equals x cubed at the point x equals a. And real quick, we can sketch this. This looks like this. And then the point we're trying to find the tangent line is right here. Now, I actually kind of cheated a little bit, and I graphed it in Desmos. This is the setup we're looking for. This is x cubed. And let me put it on the graph so when I pick it up, it'll come with me. The red line here is x cubed. The blue line here is the tangent line. We don't know the equation for it yet because we haven't quite found it. But if you notice the picture, and this is the idea of local linearization for just a second, this line, the blue line, and this red line are actually really close together through a certain point, from about here to here. these lines, the blue line and the red line, are really close together. Look at my screen right now if you're not. This line and this line are really close together. Out here, not so much. But the idea of local linearization is within a certain range of x values around our approximation, we can actually use the line to approximate the curve. And this is really useful when functions are a lot more complicated than x cubed. Right, for x cubed, we don't need to do this. Like, we can just take that value and multiply it by itself 3 times. Super simple. But when things get more advanced, more complicated, e to the negative x squared, like, we don't necessarily want to do that. So I'm actually going to bring this up with us. I put it in the blank notes. I was thinking about taking it out, but I think I'll leave it in just so you can see it too. Doesn't really spoil anything because it doesn't really give the answer. But that's exactly what I drew over here. And this is why I always encourage you all to draw your graphs. Draw what you're looking at, or graph them if you can. I happen to use Desmos to do this, and I cut off all the secrets, right? I cut off the tangent, the actual equation of the tangent line because we need to find it. But notice that we have a problem from L1. We're asked to use secant slopes to conjecture the slope of the tangent line. So we're going to go through the motions. But don't forget, don't lose sight of this. Remember concept 4 we talked about above? D4 through D8. In D4, we learned formulas for these derivatives. F prime in this case is 3x squared. So what we could do is plug in x equals a equals 1 to this function. F prime of 1 is 3 times 1 squared, which is 3. And this actually tells us what m is. This is the slope of the tangent. This is the value of the first derivative of x cubed at x equals 1. So going through the motions of secant slope conjectures, secant slope formulas to make a conjecture, we are expecting the value m equals 3. We are going to figure out a way to make the work show m equals 3, because that's what it is, using D4, right? You could also use the limit definition of the derivative. Nobody wants to do that because nobody wants to FOIL out x plus h 3 times, but still, you could. Don't lose sight of that fact. But let's go ahead and reproduce the procedure from L1. So from L1, you're required to pick 3 points to use for secant slopes. I always say just stick to the right, pick points to the right. I'm going to keep it simple, and because that's also what I wrote down in my notes. So I'm going to go all the way out here to 3, and we can't see it on the graph, but the tangent line is going to, or the secant line is going to connect to the point here, the green point, with whatever that point is up there. 3 times 3 times 3, 27. Then I'm going to bring it in. I'm going to pick something less than 3. I still can't see this one on the graph, unfortunately, but that's going to be the one here. So this is number 1, this is number 2, and then on interval 3, and you don't have to do this, but I encourage you to, pick something really close to 1, because that value you get should be really close to the tangent slope, which we know is 3. And then use our formula. The formula for L1 was the difference quotient, the slope of a line connecting 2 points, f of a and b f of b. This is a. A is always given. It's always the given value. Make sure that one stays constant. B changes. B equals 3, B equals 2, and B equals 1.001. So for the first one, x equals a equals 1, and x equals b equals 3. We have m equals f of 3 minus f of 1 over 3 minus 1. And watch this, because you need to be using the f from the original problem. I know I let you use a note card, and some people have done this. They put the x squared example on their note card, and then they're looking at their note card to do the problem, and then they forget, oops, no, you got to use this function in the given problem. If you don't, you're not going to get 3 probably. If you do, you got 3 by happy accident, and unfortunately, I'll probably catch it. So f of 3 is 3 squared, or 3 cubed. See, I even did it. F of 1 is 1 cubed over 3 minus 1. So the value that you get here is 27 minus 1 over 2. 26 over 2. And I just found a mistake in my key because in my key I only squared 3 and didn't cube it. I wrote 9 minus 1 over 2. Nope, watch out for that. So we have 13. This is the slope of the line between the first choice of B, which again is off the line. You can't see it, but this is a big number, and you're expecting that big number to decrease because you're expecting it to go closer to 3, and let's see if that happens. For number 2, x equals a equals 1, x equals b equals 2. This is m equals f of 2 minus f of 1 over 2 minus 1, or 2 cubed minus 1 cubed over 2 minus 1, or 8 minus 1 over 1, or 7. And that makes sense, right? If you had done this math and gotten a value there that was like 45, then that would be a red flag. You would be like, that shouldn't be that big. I'm expecting it, since the line's getting closer to the tangent line, I'm expecting it to decrease to 3. So then the last one, x equals a equals 1, x equals b equals 1.001, really close to 1. We've got f of 1.001 minus f of 1 over 1.001 minus 1. This is 1.001 cubed minus 1 cubed over 1.001 minus 1. And I get, when I type that top part into my calculator very carefully, I get 0.003003001 divided by 0.001, which is 3.003001, which tells us that our conjecture is most definitely m equals 3. So if I use that conjecture, m equals 3, not 3.003001. Honestly, on a checkpoint, if you answered that as the conjecture and then correctly used it to find the equation of the line, I probably wouldn't take it from you just because that was a conjecture. Like, that's what we kind of did. But ultimately, we know now what the actual slope is, so we should actually use that slope. And our work for L1 should show that that's our slope. Okay, so let's now use our conjecture of m equals 3 to create the equation of the tangent line. That's going to be the equation for this blue line here. And remember, local linearization and creating the equation of the tangent line are actually the same thing. I'm going to show you the formula in a second once we get through this, but I also want to show you that using either formula is valid. So we could use the point slope form, we just need to know what y naught and x naught are. X naught and y naught you should always use as a f of a, because that's the only point. Look at the graph. That's the only point that you know is on that line. You want that line specifically to be a tangent line to the graph of x cubed. If you use a point up here, it's not only going to be the wrong slope, but it's going to be the wrong point. So make sure you always use the x value you're given as x naught or a, and evaluate the function at a, which you've actually done 3 times already. The function value at a is 1. So x naught, y naught is 1, 1. So if I plug 1 equals y into that, and 1 equals x into that, leaving the x and leaving the y, we have to have independent and dependent variables for this line. So we have y minus 1 equals 3, which is our slope, whatever our conjecture was, or whatever our value of f prime at a was. And then simplify. Add it over after you distribute the 3. So you've got y equals 3x minus 3 plus 1. Me adding the 1 over is there, me distributing the 1 over is there, meaning y equals 3x minus 2. But if I had instead tried to do the slope-intercept form, notice that when I find b, I'm just going to be evaluating negative 3 plus 1. Y equals mx plus b. Here, we take the y value of 1 and the x value of 1, the m value of 3. We have b here. And then this x value, just like the y value was the orange value, becomes the x value we have, 1, the x naught value. And then we solve for b. And look at it, literally. b equals, so the opposite of that, b equals 1 minus 3, which is negative 2. What just happened? Why is it negative? Oh yeah, it's negative. That's exactly what we wanted. I thought it was positive for a minute. My brain wasn't working. So this is the exact same equation in the exact same line, found in a different way. Y equals 3x minus 2. You can also check your graph to make sure that this is right by looking for the y-intercept of that line. And if you had zoomed out a little bit in the graph, you would see that the y-intercept of that line is negative 2, as you'd expect. But you can't get the line. You can't get the equation on the graph without knowing the equation of the line. So don't try to look for that. You have to find it first. So in Learning Target D10, we are going to actually take that point slope form of the equation of the line. Y minus y naught equals m times x minus x naught. And we're going to reform it. And we're going to call it the local linearization. We're just taking something and renaming things, basically. I'm going to take the f of a value and plug it in here. Right, so I'm going to be, again, given f of x and x equals a. I'm going to take f of a, which is the function value at the given x value, plug it in there, and I'm going to take a and I'm going to plug it in there. I'm going to have a slope, right, but I'm going to find that slope by taking f prime at a. So I'm going to actually go through and find the derivative, whichever method I like. You can find m however you want to. I don't care if you use formulas. I'd recommend that you do, just because it's so much faster than doing the limit definition or whatever. So much faster. And then the only other change we're going to make, and this is kind of the weird one, is we're going to call the function, instead of calling it y, this is the function's name, this is the dependent variable, we're going to represent it with something different, L of x. So what we're going to have is L of x equals f of a, so I'm going to add it over. L of x equals f of a plus f prime at a times x minus a. That is the local linearization formula. That is the formula I'm about to write down in the blank below. But notice too that I can add over y naught, which is what I'm doing, which is why it's not negative there and why the equal sign quote unquote moved. So here's the definition. Suppose f, and we're going to see this in L10 again, D10 again. Suppose f is a differentiable function on an open interval I containing a point x equals a. This tells you what you're given. You have f and you have x equals a. Then the local linearization of f at x equals a is the linear function f at a plus f prime at a times x minus a. Just what I have written up here, which again is no different than the point slope form of the equation of the line. I just add over the y value. I have f of a, or f prime of a, the slope, because remember, emphasizing again, the value of a function's derivative at a point is the slope of the tangent line at that point. And again, we call this the local linearization or the local approximation because it can also be used to estimate values of functions close to A. We're going to talk about this in lecture, but I want to just come up to the top here and just reiterate that within this interval right here, within this interval of x, and this is why the definition talks about an interval of x, within this interval of x, this blue line and this red line are very close together. Very, very close together. So we could use the blue line to say, all right, I know how to find this function's derivative real fast, create the equation of this line, which takes much less computational power, finding a function's value when the function's a line than when the function's a crazy natural log or exponential wrapped up in powers or whatever. I can use that line to get a good idea of what value that function has. And you'll even learn in Calc 2 that you can go further than using lines. You can actually use polynomials to approximate functions. If you use a polynomial to approximate a polynomial, you're going to get a perfect approximation, but if you use a polynomial to approximate other types of functions, you will not necessarily.